So now we'll start talking about properties of these definite integrals. So a lot of these properties are just inherited from properties of the antiderivative in general. So these integrals are going to behave a lot like antiderivatives, and the reason for that is contained in the fundamental theorem of calculus, which we'll see in just a second. But this first property just says that if your two integral bounds are the same, then your area will be 0. So in other words, if you want the area from x equals 0 to x equals 0, there wouldn't be any positive area just above that vertical line. So because that vertical line is infinitely thin, we wouldn't have any area above a single x value. So the first property just says if your bounds are the same, your area will be 0. The second property is just saying that if your bounds are flipped over, so if you have the integral from, let's say, 5 to 0, so if your bounds are out of order, normally we would write the smaller one on the bottom and then the larger one up top. If the bounds are out of order, then what this does is it means that your sign has flipped. So this would be negative the integral from 0 to 5, f of t dt. And then the integral from 0 to 5 would be the ordinary area here. So if the bounds are out of order, you can correct that by just putting a minus sign in front of the integral there. Property 3 is just saying that if you have a constant multiple on the inside, or I should say a constant factor on the inside, you can bring that on the outside of the integral just like we would with anti-differentiation or differentiation. So this has the nice property that you can just pull those constant factors outside of these integrals, just like you would with an ordinary integral or derivative. And then the same thing is true for this fourth property, that's the linearity property. If you're trying to integrate something like f plus g, that's the integral of f plus the integral of g. And the same thing applies if you have a minus sign in between them. The integral of f minus g is the integral of f minus the integral of g. So you can split this up and integrate each of the terms separately. And then this last property might seem a little bit tricky. It's just saying that if you want to integrate from a to c, then you could integrate from a to b and then stop, and then you could integrate from b to c. So let me draw a picture for this one. Let's say that you want the area, so I'll have a curve like this. That's my f of x. Let's say that you want the area between this x value a and this x value c. What you could do is you could break this up into two integrals, which are separated at b. You could integrate first from a to b, and then add the area from b to c. And that's all that this expression is saying. It just says if you want the total area from a to c, you could take the area from a to b plus the area from b to c. So let's use these properties to compute some integrals. So in problem 4, it says if the integral from 1 to 5 of f is 36/15, then what is the value of the integral from 5 to 1? So remember that if you just flip over these integral bounds, then all that does is it changes the sign of the initial value. So remember that the integral from 1 to 5, well, maybe I'll write it this way. The integral from 5 to 1 of f of x dx. If I wanted to flip those over to correct them, then I would just need a minus sign out front. So this would be minus the integral from 1 to 5 of f of x dx. But we're told that the integral from 1 to 5 is 36/15. So this would be negative 36/15. So again, if you just flip over the bounds of integration, the only thing that changes is the sign that you would be working with. And in the vast majority of cases that we're going to consider, we're going to have the integral bounds written from least to greatest. So the smaller integral bound will be on the bottom, and then the larger value will be on the top. Next, we want to calculate the integral of this expression given each of these separate integrals. So what I want is the integral, let me change to blue because I like blue a little better. Okay, so we want to integrate from 2 to 14 this expression, negative 3 f of x plus 2g of x minus h of x. I want to integrate that with respect to x. Now, the first thing that I would notice is that we only have information about the integral of f, g, and h. We don't have information about this whole expression. So what I would want to do is break this up into as many terms as possible. So the first thing that I can do is I notice that there are 3 terms here, so I'll split up into 3 separate integrals. So this would be the integral from 2 to 14 of that first term, dx, plus the integral of the second term, whoops, that's a 2g, plus the integral of that last term. So that would be the integral from 2 to 14 of negative h. And I'm, just for the sake of not running out of space, I'm suppressing the dx. It's clear here that we're integrating with respect to x, just because x is the only variable in these functions. So this is what we have so far, but we're not quite able to compute these yet because each of these has some constant factor in front of it, a -3, a 2, or a -1. So the next step is that I would factor out those constant multiples to the outside. So I would rewrite this as a -3 times the integral of f, and then I can factor out a 2 from the second integral, so this would be a 2 times the integral from 2 to 14 of g of x, and then I can factor out that minus sign, or in other words, a factor of -1 from that last one. So this would be the integral from 2 to 14 of h of x. And again, if you want to leave off the dx, if it's clear that you're integrating with respect to x, I'm okay with this shorthand that I've used for these last 2 integrals. So if it's clear that you're integrating with respect to x, you can suppress that. But now I can fill in the values of each of these integrals because I know them from the box up above. So this would be a -3, that should stick around, but the integral of f of x between 2 and 14 should be 28. So this would be a -3 times 28 plus a 2 times the integral of g, which is 39, minus the integral of h, which was 8. And you can plug this into your calculator if you'd like. I am not going to worry about computing this mentally because I don't really care what the value is. I would be fine with this answer, honestly. So if you just want to box an answer like this, as long as this evaluates to the correct value, then I'm happy. So you do need to get rid of all of the integral signs, just like in previous parts of the class I had you get rid of all of the primes or all of the derivatives that you need to take, but you don't really need to clean up your answers here. Okay. So I'm not checking whether you understand basic arithmetic, I'm checking whether you understand the mechanics of integrals and derivatives. So I would be fine with this as your answer. And then lastly, if it is known that the integral from 0 to 8 of f is 10, and the integral from 0 to 5 of f is 5, then we want to find the value of the integral from 5 to 8. So we can do this in the abstract sense, or in terms of a picture. So maybe on the left side, let me draw the picture here. So let's pretend that f looks something like this. And we're looking between an x value of 0 and an x value of 8. What we're told is that the area between 0 and 8 is 10. So this whole area is equal to 10. And we're told that if you look at the area to the left of 5, so this area, that area would be 5. And then our question is, what's the area between 5 and 8? So what's the remaining area over here? And it's clear that if the left area is 5 and the total area is 10, then the right area must also be 5. So our answer here would have to be 5. But you can also do this algebraically using that rule that we saw up above. We know that the integral from 0 to 8 of f is equal to the integral from 0 to 5 of f plus the integral from 5 to 8 of f, using that property that we talked about a second ago, where you can just integrate from 0 to some stopping point, and then from that stopping point to the upper bound. And now we can substitute in the values that we know here. So we know that the left side is 10, We know that the integral from 0 to 5 is 5. And then that allows us to solve for the value of the integral that we want. So subtracting 5 from both sides here, we would end up getting that the integral from 5 to 8 of f is equal to 5, like we wanted. So if it helps you to think in terms of the pictures, then that's perfectly fine. But you can also, most, if not all of the time, just use algebraic manipulations to do this. So that's sort of the basics of how these integrals are going to behave. The next thing that we're going to talk about is the fundamental theorem of calculus, which sort of puts this all together and justifies why we would use the integral sign here, like we have been using for antiderivatives.